price with direction. The simplest model used for permeability distribution is transverse anisotropy. Okay, so herein the vertical and horizontal permeabilities described as Kv and Kh. All right, and typically Kv becomes lower than Kh. This we can say related to that. And when the medium is completely saturated, let's talk about the absolute permeability. For example, first of all, I would like to say that, for example, what we said, vertical permeability and horizontal permeability. So this ratio is estimated. Which ratio? The horizontal to vertical permeability ratio is estimated, and it gives a very good idea to geologists regarding on what happens in downhole, right? It helps in understanding the rock permeability between the vertical and horizontal planes. For example, a high horizontal to vertical permeability ratio states that the reservoir rock has a low vertical permeability with respect to horizontal permeability, and it resulted in produce a large pressure drop near wellbore because of vertical component of flow. So this pressure increase represents an increase in the skin due to the partial penetration. All right. So because of that, the description of these vertical and horizontal permeabilities are crucial. So when it comes to absolute permeability, the medium is completely saturated. If the medium is completely saturated with one fluid, then the permeability measurement is often referred to as specific or absolute permeability. So one fluid available in the medium. All right. Okay. So fluid saturation. So fluid saturation is the saturation of the fluid is the fraction of the pore volume occupied by that fluid, right? So it's the volume of the fluid divided by the pore volume. So total pore volume you have, how many percent as a fraction, how much of that is occupied by that fluid. So if you want to know this one, you have to use the saturation value. So basic concepts of the hydrocarbon accumulation, how it estimated in with the drawings lines. Okay, the water is a gray color and oil and gas is the black color, can be seen in here. So as you can see, there is a irreducible water saturation in which had tendency to spread on the rock surfaces. So because of that, you cannot take this water. So it's called irreducible water saturation. Okay. How we determine these fluid saturations? We use core analysis, as I mentioned. Core analysis is one of the main sources. With in situ taken samples, it will be much more healthy, much more with lower uncertainty. You can get the results actually. Capillary pressure measurements can be performed, and of course, logs is another choice of guessing this. Electric open hole logs is used for that one. Okay. For the relative permeability term, what we can say for relative permeability, before describing the relative permeability, we have to describe, of course, effective permeability. So the effective permeability, if the rock pore spaces contain more than one fluid, instead of one fluid, you have 2, 3 fluids, all right, gas, water, oil. Then the permeability to a particular fluid is called effective permeability. The measure of the fluid conductance capacity of a porous medium to a particular fluid when the medium is saturated with more than one fluid. Okay? So, when the medium is completely saturated with one fluid, then the permeability measurement is often referred as specific or absolute permeability. So what about relative permeability? The relative permeability is defined as the ratio of the effective permeability to a fluid at a given saturation to the effective permeability to that fluid at 100% saturation level, right? In other terms, for oil, gas, and water, the relative permeabilities are the effective permeabilities divided by the permeability value, all right? So when we would like to put these to a plot, relative permeability plot, here we can say that the permeability, if we have a one fluid in medium, so your permeability has to reach your Kr, relative permeability has to reach to 1, all right? In coral analysis, it can be done, okay? This can be reachable. Not exactly 1, but 0.99 can be reachable. So if oil is moving through rock with irreducible water saturation, then your permeability maximum can reach to 0.8, 0.98, something like that. All right. So herein, if water is moving through rock with irreducible oil saturation, then your water saturation level will be somewhere here. All right. So this is a scenario which both oil and water are present, and of course, if the phase is more than 1, your permeability seems reduced. All right. So we will talk about this plot also used to describe the wettability. So we will talk about this one later. So depending on the saturation, the permeability to oil and to water are each lower than 1. Thus, the effect of having both fluids present is to lower the permeability. Even the sum of the two is not unity. So therefore, when a well starts to producing water instead of just producing oil, if you start to produce water as well, your liquid production is likely to be reduced. Okay, so phase change, adding another phase, totally has an effect on your values of permeability. So what about wettability? So these terms are strongly dependent to each other. Okay. So what about wettability? Wettability can be described a tendency of a fluid to spread on a surface when that fluid and the surface also has in contact with another immiscible fluid. Two fluids are not miscible with each other. They are immiscible, and they both has to be in contact with your rock surface, okay, to have a compress. The second fluid can be air, okay, a gas phase, of course, but can be mostly we are using it for oil and water, right? Okay. So in the beginning, we said this last week. In the beginning, many rocks were water wet. Most of the rocks were water wet, and by time they become oil wet by the exposure of oil phase in the pores of them. All right. Okay. So, for example, here in the first case, you are seeing that we can say the rock is water wet. How we describe this one? The water has a tendency to spread on a surface, right? Spread on a surface. So the angle which the liquid surface making with the rock surface is, what about that? Is higher than sorry, not higher than, lower than. We are taking this theta, this as theta, lower than 90 degrees. So because of that, we can say it's water wet rock. So when it comes to oil, we are taking this part, all right, as a contact angle. So it's more than 90 degrees. So oil has a tendency to say this water. Another explanation here. So in the water phase, the theta, as I mentioned, it low. How much it increased? For example, here we can get something close to 0.7, right? 0.6867, something like that. So we can consider that this is strongly water wet rock. It can give a rough idea, of course. It gives you a rough idea, not exact idea, but you can say that it shows that it's strongly water wet rock. If you are in the laboratory, you can say, let's make some core analysis for this one. And see, it seems strongly water wet dry, but let's describe this one. So you can perform some wettability analysis like galvanometric measurements, or some core analysis like USPN and Amot method. And there is another alternative method that we developed also in Istanbul Technical University, and the continuum of that in Abu Dhabi, the Petroleum Institute. We developed this alternative method called the rising core method. It gives you also an idea regarding on your rock behavior with the oil and water phase, with the existing oil and water phase. So in the second one, strongly oil wet rock, it says. Why? Because the water and oil cross-sectional part is around 0.4. In around 0.4. So we can say that it is strongly oil wet. We can describe, but it's a rough description, right? Okay. So the capillary pressure. Let's describe the capillary pressure as well. So herein you have a capillary tube. You have a think that you have a capillary tube, and your drop, your liquid phase and your gas phase. Let's say liquid phase and gas phase, or oil and water. Here is oil and water. Say your water phase makes an angle like this. Okay, we say this theta. This is the theta. All right. So it has a radius, it has a height of your column. Okay, and also this one way of description. The second way of description, your interfacial tension of your water and oil phase, of course, and your cos theta divided by R, your radius. Okay, so this gives you the capillary pressure. So let's describe this. Let's make it a little bit more understandable. For example, if you place a capillary tube into a dish of water, okay, then the water will climb up the tube some distance. The force which causes this to happen is capillary force. Okay, at the top of the fluid column, the shape of the fluid is cupped. Okay, the shape of the fluid is cupped, indicating that the air pressure is higher than the water pressure. So here in the previous example, oil pressure is higher than the water pressure, right? Okay. So the difference in the air and water pressure at the curved interface is called the capillary pressure. If the capillary tubes of different diameters are placed into the dish, the water will climb the highest in the smaller tube, and the curvature will be greatest, and the capillary pressure will be highest as well. So in a rock, when we talk in a rock surface which is contact with two fluids, is originally saturated with water. As oil begins to rise upwards, at the interface of oil and water in the pore space, the oil pressure is higher than the water pressure by the capillary pressure. If this oil-water interface is high above the free water level that we talked last week, which means the level of water in the dish, okay, the capillary pressure will be higher. Okay, so what this mean? This means oil moves more easily than water through a water-wet rock, since it follows the big pores and permeable paths. The water clings to the sand grains surface, and it's harder to move through the thinner passages. Okay, in a porous medium. I'm talking about the micro scale. Okay, not macro scale, it's micro scale. Okay. All right. So another term, the capillary pressure, is non-wetting phase minus the pressure in wetting phase. The pressure difference between non-wetting phase and the wetting phase, right? So it's described by Young-Laplace equation, and herein you can see liquid surface tension. Okay, or we are assuming that here it's not oil, liquid with air, contact liquid and air. Your capillary pressure term in here. And your radius, of course, R1 and R2, principal radius of curvature on the interface, it says. Okay, so difference of these R's gives you the capillary pressure term. On the other hand, we said this interfacial tension, cos theta in a tube, and your R divided by your R also gives you the capillary pressure. Will be okay. Okay, so we try to describe the main terms, and now let's go to the 5 fluid types and fluid behaviors we will move. Okay, so 5 fluid types. What are these fluids that we are dealing in reservoir and wellbore, in production, totally, in oil and gas industry? What are these? So we have black oil, first of all, okay? The easiest part, actually. We have black oil. We have certain correlations to describe the black oils, and things are easy for black oils, okay? Black oil. Volatile oil. Actually, we can say retrograde gas. We can say wet gas and dry gas from oil content. If we make it in an order, from oil content, we can say black oil, volatile oil, retrograde gas, wet gas, and dry gas. Okay. So let's start with the assumption of we have a single hydrocarbon compound. If I have a single hydrocarbon compound, my phase envelope will be like in this figure. All right. So your vapor pressure curve will be a line up to your critical point, the upper part, the above part of this point will be liquid totally, okay? Then following the critical point at a certain temperature, when the temperature increase, it will be gas phase directly, and the below part of this vapor pressure curve also will be described as a gas phase. Okay, this is single hydrocarbon compound. Let's say methane, for example, right? But in the nature, in nature, it's not like this. So in nature, we have a mixture. In most of the cases, we will have mixture, right? So what happens in the mixture? So a typical behavior of a mixture can be seen in here, the pressure temperature behavior, okay? So you have a bubble point pressure curve, okay? Not line anymore, it will be a curve, your bubble point pressure curve up to your critical point, all right? And then following the critical point, your D point curve starts, okay? Because it will pass through gas phase directly, your D point curve starts, okay? Above this bubble point curve will be described as liquids. Again, in a certain temperature, above your critical point, it will be described as gas phase. And following the lower part of your D point curve will be described as gas phase 2, all right? So inside of this phase envelope, your liquid level will increase from 0 through to 100%, okay? And these curves, this liquid percentage curves also, of course, varies according to your hydrocarbon content directly. So in this example, for example, it's a good case. It's a typical case, but good case. The A point in here gives you your reservoir pressure and temperature. Okay. So B point, for example, we can describe this as your wellhead pressure and temperature. And C, separator conditions. Okay. So what happens in here in this scenario? Your reservoir pressure and temperature, your fluid is in one phase, right? The liquid phase. So when it comes through to the wellhead, it remains in one phase too. This is an easy case. So when it comes to separator, what happens? In a certain point in your pipes, it will pass to two phase directly. So what happens here, if you would like to you are taking samples, right? You are taking samples, and in your well, you have a certain situation like this. It's expected to be make a decision. what type of decision can be made? Okay, because you will take samples in your well, and you have to make a cost-effective. You have to select a cost-effective way. So, if you're a guy working in a service company, you suggest your client to take a sample from your reservoir or your wellhead or your separator conditions. It will be, let me answer this one. It will be directly, you can take wellhead samples because it will be representative samples because it's still in one phase in your wellhead. But in separator, not. Separator samples will not be representative. You have to take these ones to your laboratory and you have recombined that. It will increase the error percentage, of course. So in this scenario, it's better to take in wellhead to make it cost effective as well, because reservoir sampling will be 5 times, 6 times more costly. Okay, will be costly compared with the wellhead sampling. So B point, taking the samples from B point will be beneficial in here. Okay. So let's describe. Yeah, this was the typical phase diagram we set in previous example. This is too much like to that scenario. This is black oil sample. So in a black oil, you have your bubble point line. In most cases, your reservoir pressure temperature will be, not in most cases, in all cases, your reservoir and pressure, temperature and pressure will be indicate one phase flow. In some conditions, when it reached to wellhead, you can pass your bubble point line and you can start to produce with two phase. Okay, if you are in two phase, then you will go for reservoir sampling. If you are in one phase, you will go for wellhead sampling directly. Of course, your liquid level will be lower when it comes to your temperature will be lower. So because of that, when it comes to the surface, it will be lower and lower. Okay. This will be your separator conditions. I think there is a mistake in here. This will be your separator conditions. I think it can be somewhere in here. And when from separator, what happened? It participated your free gas and your oil. You will take it to stock tank, right? You will take it to stock tank, and your oil will be dead oil. From now on, if you take it to stock tank and wait for 12 hours, your oil will be named as dead oil. And because some more gas, which was in solution gas previously inside your oil, will be go out as well. So directly it will be named as stock tank dead oil. All right. Okay. So this is the typical behavior of a black oil phase diagram. The second one, the volatile oil. What happened? The phase envelope becomes higher, right? Becomes higher, you can say. When you compare this one, your phase envelope becomes higher. Of course, what happens in most of the cases when you come to the wellhead from your reservoir, in your reservoir you can be in single phase. But when it comes to wellhead, it will probably be two phase flow. All right. So you have to consider this one with few amount of gas, but two phase. Okay. So this is dry gas. This is dry gas. This is another. Okay, we were going according to the oil level, but no problem. So for the dry gas, what happens? Your phase envelope become very low, right? Very small phase envelope you have. So the chance of having in liquid phase is very low, right? So your reservoir condition will be totally gas. And when it comes to your wellhead, it will remain in gas phase as well. When it comes to separator, it will remain in gas phase as well. Okay. So it will be very hard to pass to liquid phase in dry gas reservoirs, and the behavior will be like this. Totally reverse of liquid, right? So what about wet gas? Wet gas is a condition which is between the dry gas and the retrograde gas. So your phase envelope, when you compare it with the dry gas, see it was very low. When you compare it with that, it's still low, but compared with dry gas, bigger, right? Bigger diagram you can see. So you start to see your bubble point line. Okay, your bubble point line is very low in here. So you start to see your bubble point line. Of course, the point line is much more compared with that. But in most cases, your reservoir pad, your reservoir pressure temperature is still in gas phase. And when it comes to the wellhead, you still stay in gas phase, and separator conditions, you will see some liquids. Okay, in wet gas, you will see some liquids in separator conditions. Few amount of liquids, but there will be some liquids, so separation is needed. You cannot send it directly to stop them. Okay. So the retrograde is between volatile and wet gas. Okay. So you can understand from the envelope as well. So in this one, when it comes to the separator, again, you will be in single phase. You will pass in somewhere in your wellbore. Okay, you will pass to two phase. And when it comes through to the wellhead, it will be somewhere between 10 to 15%. Okay, so when it comes to separator, it will be somewhere in 5 to 10% liquid. Okay, so this is the typical behavior of retrograde as well. So three gases, what are the differences we said? So for dry gas, gas at surface is same as gas in reservoir. Totally. So where I can take my samples, I can take it from the separator, from the wellhead, doesn't matter, from the reservoir, but cost-wise, what is the best one? Separator. The easiest and the cheapest, separator. You will take it from separator directly, okay? Wet gas, recombined surface gas and condensate represents gas in the reservoir. Condensate is produced, of course. For the retrograde gas, recombined surface gas and condensate represents the gas in the reservoir, but not the total reservoir fluid. Very few amount of gas you can see in retrograde in the reservoir. When it comes through to your wellhead, so it will your gas phase will be the dominated one, and the liquid will be very few amount. Okay. So what is the choice herein? Actually, the best choice if you want to take representative reservoir samples, if you want to make a representative sample, you have to take your sample from your reservoir directly, because this in here, it will not be representative because it will be in two phase. Recombination is needed. So the best choice is to take your samples directly from your reservoir. For example, what happens? One another thing. You have to take your samples in pressure-assisted sample cases, right? Samplers need to be pressure-assisted. For example, herein, you have certain pressure and temperature value, but you have to, when you are taking this through to your wellhead, you have to stay in one phase. You want to make your reservoir sample representative, right? So you are taking to the wellhead, but you want it to stay in one phase. What you need to do? You have to keep your pressure in your reservoir pressure level. So because of that, what you will do? You have to use pressure assistance. Some service companies has very good tools for this. They are using nitrogen assistance. When it takes the sample directly, nitrogen assistance, it closes the chamber and nitrogen start to work. And when you take it through to your wellhead, it will not be like this. It will stay somewhere like this. Okay, stay somewhere. Of course, the temperature, of course, decrease. It will stay somewhere like this. All right, it keeps you in one phase, and when you take it to laboratory, you can directly use that sample in one phase in reservoir conditions. This is very beneficial one. Okay. So mentioned this one. Okay. So I wanted to put this slide as well to see all the 5 reservoir fluids in one picture. So black oil, we said typical behavior. Volatile oil will have more phase envelope. Retrograde gas, phase envelope will be lower, but it starts to pass to gas phase. We can see liquid level will be lower. And when it comes to wet gas, your phase diagram will be smaller, and your bubble point pressure curve will be very low. And in the gas phase, it will be much more lower. And of course, phase diagram is lower compared to wet gas. So let's make some points regarding on the field identification. Okay. For example, for black oil, volatile, retrograde, wet, and dry gas, okay, for initial producing gas oil ratio, GOR values, for black oil, it will be lower than 750. For example, I was working in a field, black oil field, Rumeila, called in Iraq. We were maximum reaching to 1,500. Okay, so typical black oil reservoir, and it has 1,200 wells, something like that, all producing same. So all the correlations are directly applicable for this type of reservoir. It's the easy one. So when it comes to volatile oil, it will be between 1,750 to 3,200, your GOR value, all right? If it is more than 3,200, you classify it as retrograde gas. If it is more than 15,000, you classify it wet gas, and dry gas, it's of course more than 100,000, okay? So the liquid gravities, for black oil, it will be lower than 45, okay? For volatile oil, it will be higher than 40. Retrograde, higher than 40 again. For wet gas, you can get results up to 70. And in dry gas, you have no liquid, of course, right? What about the colors? If you see a very dark color, you can classify from the view. You can classify it. I think it's coming from me, or it's not coming from me, right? Okay. So for colors of stock tank liquids, so if it is in dark color, you classify it as black oil, you can. Some colored, some greenish, you can see dark greenish, maybe. You can classify it as volatile oil. For lightly colored one, retrograde gas, water white, wet gas. And if you don't have any liquid for dry gas, so you cannot classify it, okay? So this can be, this can give you some rough classifications, okay? Field classifications in the well site. For the laboratory analysis, phase change in reservoir. So for black oil, bubble point curve, remember. Volatile oil, bubble point curve. A retrograde gas, dew point curve, the other part, dew point curve. For wet gas and dry gas, we are already in gas phase totally. There is no phase change, okay? For heptans plus, which means C7 plus, right? C7 plus. More than 20% of all will be C7 plus for black oils, more heavier components, right? For volatile oil, it will be between 12.5 to 20. Retrograde gas will be lower than 12.5. Wet gas lower than 4%. And for dry gas, it will be lower than 0.8%. For oil volume factor at the bubble point, it will be classified just for, of course, black oil and volatile oil. So if it is lower than 2, we can say that it's black oil. If it is higher than 2, volatile oil, we can say, of course. Okay, so let's see all in one plot. Okay, this is C7 plus in reservoir fluid as a mole percent, and the comparison with the initial producing gas oil ratio (GOR). All right. So, but we said in your dry gas, if you are in dry gas, your GOR will be very high, right? We said here is 50,000. It can reach up to 100,000 as well. Okay. So we cut the plot in here in 50,000. So your dry gas area can be described in this section. Your wet gas will be according to the when you compare your wet gas, when you compare it, it is let's say this is 5%. Okay, sorry. Let's say this is 5%. So up to 4%, you describe it wet gas. So between 4% through to 16% retrograde gas. Okay. So for volatile oil, the range is higher compared with that, and some part of this range is also black oil can show. It's between 16 up to nearly, we can say 22%. And from when we say sorry, this is 12.5, of course, I remember. This is 12.5. This is 17.5 to 30% and more. We can classify it as black oil. Okay. All right. So let's talk about the production trends for these 5 fluid types. Okay. So primary production trends for the GORs, for the API chains, for 5 different fluid types. For example, for black oil, by time with the production, you will see in the beginning, in the earliest times, it will be steady. It will not change a lot. But later on, in mid range, it will start to increase. Okay, your GOR will start to increase in a certain level, and after that, it will remain constant for a shorter time, and it will start to decrease. Okay, it will start to decrease. For volatile oil, and let's continue with API and black oil API. Black oil API value will show us a slight decrease, okay, by time, and then show a little bit increase. Okay, it will be, range will be 5, maximum 5 API difference. Okay, not too much. Maximum 5 API. So for volatile oil, when we can, of course, I am talking here. There is no, okay, the water production will change everything. I'm talking here just the black oil production. Okay, this one. So for volatile oil, your GOR in the earliest time will remain constant, and then it will slightly start to increase, and then it will show similar behavior but more smoothly compared with the black oil one, right? It's more smooth of black oil, and then shows a little constant value, and then slightly decrease. It will pass. And the API show slightly increase as well. Okay, so show a slight increase. Sorry, show a slight increase. For retrograde gas, compared with the black oil and volatile oil, the GR will remain constant more. Okay, will remain constant more, and then start to increase, because gas will be start to be dominant phase by time as well, right? So API also will show a constant value in the beginning, and it's very similar to GR value, compared with GR value, the behavior, and start to show an increase too. So for wet gas, think about that. Gas is already a dominant phase. Okay, already a dominant phase. So there is no, it's already in high values, and the liquid level is very low. So it will remain constant, the GR value, and your API also will remain constant. Okay. For dry gas, you don't have any liquid to compare. All right, by time. Okay. So for a single component, I have a single component again. All right. Let's talk about the pressure and volume behavior. All right. In a PVT cell, we are talking about. I have a single component. I took my sample, put it to laboratory, and I am now what I am doing. I am comparing the pressure and volume changes in a certain temperature, right? So if it is in the first one, in the number one, you are seeing all in liquid phase. Okay, we have an oil and all in liquid phase. Okay, so I see the first. Okay, the pressure start to decrease by the machine. What happens? It's piston comes to backside, and the first bubble, first gas bubble seen, and we describe this pressure as bubble point pressure. All right, and then we continue to lower the pressure by using the piston, and certainly it reaches to 0.3, D point. What is this? The last drop of liquid. From this point, there will not be any liquid more. Okay, there will not be any liquid. So I continue to take the piston more and change the volume and decrease the pressure. So what happens? I reach up to fourth part. So all I am in gas phase. Okay, starting from the third part through to fourth, I am in gas phase totally. Okay. All right. I already mentioned this one, the separator conditions. Okay. So separator conditions, what happens? Your pressure and temperature decrease. When your pressure and temperature decrease, your point in your wellbore will become to somewhere like this. Okay. Because it's both decreasing. So it will be volatile. Volatile will be like this. Retrograde, wet gas. Wet gas is very important in here because the phase is changing, right? From gas phase, when it comes to separator conditions, in mostly what happens, you are passing to two phase. So if you are producing wet gas, you have to be very careful. You have to use a very good separator. This is also important. The quality of your separator is crucial. And when it comes to dry gas, it's already you are in gas phase. It's not harmful. There is no problem. You can take your sample anywhere you want. Okay, you will choose the most cost-effective one. Okay, so let me open all because we are online now. Okay, so oil change during production. So during the production, there will be a losing. There will be a mass losage, right? The oil phase will lose its mass. Gas come out of solution on trip to surface. Okay, you start from your reservoir, you're coming to your wellhead. Of course, with the decrease of your temperature and pressure, solution gas will expand and pass to gas phase. When it comes, you reach to your wellhead. From your wellhead, when you're going with your pipes through to the separators, of course, through to the separators. Again, there will be some pressure, temperature change. With this temperature, there will be some, of course, some more parts which will pass from solution gas inside your oil through to gas phase directly. Okay. So because of that, next week we will talk about this one in multi-phase flow metering. What happens? The industry solve this problem. Because when you are going from your wellhead through to your separator, it will take some time and some length of your pipe, right? So what happens? Multi-phase flow meters in line conditions enable to take some samples even and some measurements without separating these three phases. It's being your line, and it's taking the samples directly from your line. Okay, we will talk about this next week. So, so it loses its mass. Another thing is the contracts. The temperature decreases from reservoir temperature to 60 Fahrenheit. Averagely, we are assuming that it's 60 Fahrenheit in atmospheric conditions, we are saying, right? Okay. It expands. Pressure decreased from the reservoir pressure to the atmospheric pressure. This resulted with the things that I mentioned already, right? It expands, gas phase come out. We have actually 4 main steps, right? From your reservoir, you come to your wellhead. From your wellhead, you come to your separator. You separate your fluids. Your liquids comes to your stock tank and becomes dead oil. Minimum staying in there 12 hours becomes dead oil. And some part of the solution gas also reveals and pass to gas phase, and your oil remains in there, right? So 4 different phases, 4 different stages we have. In these 4 different stages, it loses its mass, it loses the temperature, it expands because of the temperature decrease. Okay. All right. So fluid physical behavior. So oil, in the absence of gas in solution, is called dead oil. I mentioned this. The physical properties of dead oil are a function of the API gravity of the oil, pressure, and temperature. The API gravity of oil is defined as, we already know, all of us, is 141.5 divided by specific gravity at 60 Fahrenheit. I saw some field engineers who are taking in separator conditions, in stock, not stock tank conditions. So this is actually one of the crucial points. Okay, minus 131.5. Okay, it's very clear, very easy. API gravity classification. So with gas in solution, oil properties also depend on gas solubility. Gas solubility is normally represented by RS. Okay, RS. If you see RS, it means that the gas which was inside your oil with a certain pressure and temperature and comes out from your oil phase as gas phase. Okay. All right. So the gas solubility is defined as the volume of gas dissolved in 1 stock tank barrel of oil at a fixed pressure and temperature. Okay. In other words, we can say that it's a measure of your 1 barrel of reservoir oil. When it comes to surface, what happens? Okay, how much barrel of oil it represents when it comes to surface. This is the classification of this ratio. All right. So there are several in the literature. There are several correlations for gas solubility. For example, you are seeing here the standing correlation, which is used widely and very useful one, easiest one. Okay. And there are some others like Lasseter and some more. Most of the, for example, most of the softwares are taking this for black oils, of course. This will be used for black oils when it comes to volatile and so on. It will show some error percentage, but for black oils, it's very useful and can be used. Okay. Can be used without taking any sample section. Oil formation volume factor, volume of reservoir oil at reservoir condition required to produce 1 standard volume of stock tank oil. The unit is reservoir barrel per stock tank barrel. The ratio of reservoir barrel per stock tank barrel. The symbol is BO for oil, right? BG for gas, of course. So, okay, we are seeing here these 4 stages. These 4 stages directly. So what happens? You have an oil phase, and in your wellbore somewhere, okay, for example, let's say this is 2000 meter, and in 1000 meter, it shows a flash. What do you mean? It passed to 2 phase. Okay, it passed to 2 phase. When it comes to surface, it's coming as 2 phase, right? So we saw this in retrograde, right? So it comes to your wellhead 2 phase, and of course still you have an oil phase, but this oil phase also has some gas in it, of course, but it could not come out because of the pressure and temperature. When it comes to your separator, some part of this also joins to this free gas volume, and then from separator, your liquid phase comes to your stock tank, and from your stock tank, some part of this more comes to gas phase, pass to gas phase, and this will be your dead oil. Okay. So typical shape for oil formation volume factor can be described like this. A certain slope in the beginning you can see, and then a slope as well for a long time. Okay, for a long time means, of course, you will see in the time of course you will see this because pressure is changing. So when your pressure increases, your PO will be like this. But after that, when you reach to your bubble point pressure, what happens? It will start slightly to decrease. Okay, it's a typical behavior. And then let's talk about solution gas oil ratio. I will open all of these. Sorry. So volume of gas which comes out of the oil as it moves from reservoir temperature and pressure to standard temperature and pressure. Solution gas oil ratio. The unit is cubic feet of total surface gas at standard conditions per barrel of stock tank oil at standard conditions. Okay, standard conditions cubic feet divided by stock tank barrel. Okay, so the typical behavior for the solution gas oil ratio also up to your bubble point, it will nearly same, but your, of course, the change of your slope will be earlier compared to another one, the previous one. When it comes to your bubble point pressure, it will remain constant. Okay, slightly decrease, but it will remain constant. We can say, okay, very slight decrease. Okay. So, if your reservoir pressure is higher than your oil bubble point pressure, okay. So this is this was the first case. We said I already described this one. This condition means that your reservoir pressure is higher than your oil bubble point pressure. You are in one phase in your reservoir and coming to two phase along your wellbore or in your wellhead. In your wellhead it can be as well. Okay, but if your reservoir pressure is lower than your oil bubble point pressure, then what happens? You have a free gas. You have a free gas in your reservoir too. Okay. Not only in surface it's existing as a solution, you have a free gas in your reservoir too. So you have to, in this case, what you need to do, you have to calculate your BG, okay, gas formation volume factor as well. Okay? You have to consider this as well. Okay, near of your oil formation volume factor, you have to consider your gas formation volume factor too. Okay. This figure, last week also we talked about this one, right? We talked about this one. So, okay, BO, BG, B water also, or water formation volume factor as well, because water has a solution vapor in it, right? So solution gas in it, and it passes to gas phase when it comes to surface as well. So not vapor. Vapor is different condition. So we can say that we have to consider all these values when we are extra values when we are making our calculations from reservoir through to the surface, through to wellhead, through to separator, and through to your stock tank. Okay. So what about oil viscosity? This is another property of fluid which is very crucial. The oil viscosity. The viscosity is the resistance to flow exerted by a fluid. Okay. So large values of viscosity, large values of oil viscosity, what happens? Resulted in having low flow rates because the resistance will increase, your resistance will increase, and the movement of the particles will be slower and slower, so it will directly affect your production. Okay, so the unit of viscosity is centipoise. Pascal second also can be used, right? And the symbol is mu. For oil, it's given here. So see, for example, it shows a quite high viscosity here, right? The example shows a quite high viscosity. When we compare the viscosity in centipoise with API gravity degrees, we can say that, for example, yeah, it's the different materials viscosity values has been given in here, and API degrees of oil gas behavior is given as well. Okay, so we can say that here we classify oil, right? So ketchup, so you can see ketchup here. Ketchup is in the mid-range of an heavy oil, right? We can say. So there's a comparison table has been given in here for the aim of giving an idea to you. Okay, what happens with the dependence of oil viscosity on pressure? Let's see this one. What happens? So the typical behavior of viscosity with increasing pressure will be like this. Okay, the slope it changed the slope and so shows an exponential decrease by time till when it reached to your bubble point. When it reached the bubble point, it directly changes the behavior and starts to increase linearly, right? Instead of showing the exponential decrease, change the behavior and starts to increase. Okay. So another thing is fluid compressibilities. In isothermal compressibility, the formula can be described as, can be seen here, as the function of the volume and the volumetric change with pressure, of course. The unit is PSI 1 minus 1, has been taken in oil industry mostly. For oil, it's between 5 to 20 times 10 minus 6 psi minus 1. For free gas, it's 200 to 1000. For water, it's 2 to 4 times 10 minus 6, of course. For the rock, we can say 3 to 10 minus 6 psi we can take. Okay, pore compressibility, say, but it's rock compressibility. Okay, so for the total compressibility calculations, what you do in the nature, of course, all these fluids can be seen inside a pore space. So in here, what you will do, you will take your oil compressibility with your oil saturation times oil saturation plus gas plus water, and then you will add your pore compressibility. Let's say pore compressibility, it look like this, same thing in here, and it gives you your total compressibility. Okay. Okay. So volumetric gas reservoirs. So herein, sorry. So herein, the reservoir type of in this type of reservoirs, volumetric gas reservoirs, the reservoir type is it is a gas reservoir with no aquifer. There is no aquifer in it, but and it's a gas reservoir. So the main source of reservoir energy, we can say, the expansion of the original reservoir gas. Okay. In this type of reservoirs, the expansion of reservoir rock and the original water are always present, but often shows minor sources of reservoir energy. The dominated mechanism is the reservoir gas diode. Okay. So reservoir rock and fluid expansion can be important sources of reservoir energy for abnormally high pressure gas reservoirs. Okay. It shows type production characteristics compared with the gas reservoirs. Okay. So gas reservoir dry mechanisms. Okay. So gas reservoir dry mechanisms divided into two types. One of them, as I mentioned, volumetric reservoir. So here the dominated phase is the gas phase, gas expansion drive, also it's called. And the second one is the water drive. Okay, you have a aquifer. You have an aquifer in the below part. So your aquifer applies an extra pressure. Okay, so let's see the behaviors of how it behaves. Okay, how this type behaves. Okay, for example, you have three different reservoirs in here. Okay, one of them is solution gas drive, second one gas cap drive, and the water drive. Okay, so in your solution gas drive, your pressure slightly, okay, we can say that it shows an exponential decrease like this. Okay, but in the beginning it will be linear, and then earliest times are linear, and then it starts an exponential decrease. When your GR value start to increase, and it shows a drastic increase at a certain value, it shows a drastic increase, and then drastic decrease. Okay, in solution gas drive. So for the second reservoir, the pressure shows close to linear, but not exactly linear. Shows a decrease directly, and GR value shows an exponential increase. Okay. This is gas cap drive, gas assistance. If you have water assistance, then your pressure, what happens? Your water, of course, what we said last week, the energy, the potential, the pressure assistance of water compared with the gas is much more. So because of that, what happens? Your pressure drop will be lower compared with the gas ones, right? Pressure drop will be lower, and then after a while, if your water drive is enough, after a while it will start to remain constant after reaching a certain value. So your GR value also shows a slight increase by time. Okay, what about the recovery factors of these different reservoir types? For the solution gas drive, the range is between 5%, the recovery factors is between 5% to 30%. Okay, sorry, 5% to 30%. Averagely, we can say it's 15%. The gas cap drive, 15 to 50%. Averagely, it's taken as 30. When you don't have any idea regarding on reservoir properties, and you want to take some values to put it as an input to your software, right? For example, you have to take it as an average value 30. So for water drive, it's between 30 to 60. You can get it averagely 40 because most of the reservoirs with water drive is close to 30-40%. Okay. So gravity drainage drive, if you are talking about gravity drainage drive, it has a very wide range. It's between 16 to 85, and averagely we can take it as 50. We don't have any idea regarding on its behavior. Okay. Of course, this using average values will increase your uncertainty and your error percentage directly. Okay. So this, when it can be used in earlier times, if you don't have any idea in earlier times of your reservoir, in your exploration phase, you can use these values, but later on you have to correct this one with your measurements and your the data that you have taken from your tests, your wireline test as well. Okay. So for volumetric gas reservoirs, the range between gas recovery factor, of course, I'm talking about, the range between 70% to 90%, and the average can be taken as 80. For water drive, in this type, if we are talking about gas reservoirs, water drive, it's between 35 to 65%. Average it can be taken as 50. Okay. So up to now, we described the oil reservoir, solution gas drive, gas cap drive, water drive, and gravity drainage as well. Gas reservoirs, volumetric gas reservoirs, and water drive reservoirs is described as well. Okay. Now, so what has to be the favorable properties for oil recovery? What we want? what scenario is the best for us? Okay, so let's see this one. For example, if you are producing from a gas cap dry oil reservoirs, so your favorable oil properties has to be low oil density, of course, low oil density. So lighter oil, you have to produce lighter oil with larger API values, right? So it will result in having higher recovery. So low oil viscosity is another one. Okay. So low oil viscosity values means less viscous oil, more movable oil, so you will get higher recovery. High oil bubble point pressure. High oil bubble point pressure, of course, it also reaches you to higher recovery. Why? Because if your bubble point pressure is higher, when it comes through in your wellbore, it will stay in one phase, will not pass to two phase. So it will increase the amount of your oil, producing oil, compared with the two phase one. Okay. Also, oil with oil with higher bubble point pressure usually has higher solution gas oil ratio. We call RS when it comes to surface. Of course, it will be in one phase. When it comes to surface from your separator and it reach to stock tank, you will have higher RS value. In this case, gas phase will be included inside your oil phase because of that, of course, and higher oil formation volume factor. Okay. So, if we are talking about gas cap drives, oil reservoirs, the favorable properties will be, for example, the first one will be large ratio of gas cap volume to oil zone volume. All right, gas cap volume if your gas cap volume is higher than your oil zone volume, it will result in having a good pressure assistance from your gas phase. Okay. Another one is, as I said, larger gas cap is always preferable. It gives you a higher oil recovery because it pushes your oil through to your wellbore and helps. It can create a kind of sweeping effect and helps your oil to produce. Okay, because of this is something that we want in gas cap drives. If there is a gas cap, so high reservoir dip angle. So larger the reservoir dip angle assists gravity drainage of oil, so it will result in having high recovery. Thick oil column, of course, will be one of the reasons. If you have a thick oil column, it will be also good for your recovery. If you have, instead of having a thick oil column, you have a thin oil column, for example, a couple of meters, okay, you have a couple of meters zone. So what it will be resulting in having early gas breakthrough. So because of that, you will have lower recovery. Okay. So what we want gas breakthrough becomes as much as longer time to reach to the well, and a good sweep efficiency, good sweeping effect. Okay, sweeping effect is the main thing. Because of that, we cannot reach it in solution gas dry reservoirs. So because of that, here it's the reverse. We don't want it, but here we definitely want it. Okay. So what about the water dry oil reservoirs? So large aquifer, of course, large aquifer is always something that we need. So it enables better pressure maintenance and support from the beneath part. Okay. Better pressure maintenance and support, which result in higher recovery. Okay, so low viscosity of oil is something that we want as well. Highly viscous oil will result in what? Water fingering through to the reservoir and bypassing the oil phase and reach to the well. Okay, if it increases, it will be water coning, but in the beginning it will result in water fingering. So these things we don't want. Because of that, your oil viscosity is lower, means that your oil is removable. So it's a very good advantage. Another thing, high relative oil permeability and low relative water permeability. This is another thing. another meaning of this, in other words, we can say that your oil has to be more movable than your water. Okay, so it will enable a very good sweeping effect, and then you will produce more and your recovery factor will increase. So a little bit, of course, it has effect. What is this? Reservoir heterogeneity and stratification also has an effect on this. For example, more heterogeneous reservoirs, reservoir quality variations, permeability variations, can be resulted in lower recovery, of course. And more layered reservoirs, for example, like bypassing oil or non-swept layers, in the occurrence of non-swept layers, also results in lower recovery. So these type of things we don't find. Combination reservoirs will have recovery characteristics similar to those of the dominant reservoir types. Okay, which one is the dominant phase, gas phase, oil phase? According to that, it will shade. Okay, so for combination drives, we can say it like this. What about the gravity drainage oil reservoirs? For the gravity drainage, high reservoir dip angles, actually similar to gas cap drive oil reservoirs, high reservoir dip angle will be result in favorable permeability distribution. Okay, if your permeability distribution is good and have lower uncertainties, then this is something that we want. Okay, so high permeability along the dip you can reach as well. So it will result in having high recovery. So if you have higher vertical permeability, also it will result in having higher recovery. Okay. So another thing is large density difference between the segregating fluids, oil, gas, and water, of course, oil and gas, or water and oil, we can say. The large area of segregation is another another factor that we can talk. This will be resulted in having large recoveries, high recoveries. So another thing is large area over which segregation may occur. Okay, low oil viscosity, low withdrawal rates are another factors that resulted in having higher oil recovery. Okay, so these are the things that we can say regarding on the combination drive and gravity drainage reservoirs. So okay, so of course, also we can say that the abandonment pressure for gas reservoirs can be reduced by lowering surface back pressure. Gas compression is often installed for this purpose. Okay, and favorable properties for water drive gas reservoirs also are similar to those in water drive reservoirs, having large aquifers and small degree of reservoir heterogeneity and stratification. Okay, these are the things that I can say for the second week. Okay, the fluid properties and behavior. So this information, this basic information will be, I believe that for these 2 weeks, it will be very beneficial for the third and fourth week. The description of the operational tools, how we are using these tools, and the effectiveness of these tools. Okay, so it will be very beneficial. So first 2 weeks, I wanted to give these brief descriptions and the basics regarding on reservoir geology, fluid properties, and behavior. Hope that you enjoyed this course. If you have questions, I will be glad to answer your questions directly. All right.
Firstly, thank you very much for giving that informative and useful informations. So guys, if there is some question, please don't hesitate to ask. Let's wait 1 minute. If will not be any question, we can leave. Thank you again, Mr. Jawad. Welcome.
Thanks from my side. I am seeing here that there is one question regarding on the water fingering, right?
Yes, I'm also.
Okay, let me describe this one. So in certain conditions, like you have a very viscous oil, okay? Think about the Zift, asphaltene, okay? You have some asphaltene like oil, very heavy oil, okay? And your water is so much movable, okay? Compared with that oil. So you have a certain pressure coming from the down part. You have an aquifer, you have a pressure assistance. You have a certain amount of water coming from the down part, okay, to a heavy oil section. So because of that, what happens? Your water phase is not succeed to push your oil phase, okay, because of the viscosity difference. It cannot push your oil phase. Like as if, so for example, you have some asphaltene, right? You saw some asphaltene previous. Pour some water on it. What happens? See, okay, there will not be any the effect of it will not mix. It will not have any effect. Water will be very lower. Will have very lower viscosity compared with that one. So water cannot push. So what happens? Water starts to go through to the upper parts by creating some waves, okay, local waves, okay, this part, local waves, and start to, because of the pressure difference, it has a tendency, the water phase has a tendency to go to reach through to the valve, okay, and because of the viscosity difference, it's making it very easy. How? By creating these waves, and these waves seems like fingers, okay, because of that it's called water fingering. When it how I can say, when this difference becomes too much, then these fingers became higher, and then it becomes a kind of water coning, okay. Then after a while, what happens? You cannot produce any oil. It stops directly. You cannot produce any oil. Then you stop directly producing your water up to 80%, 90%. I saw someone like this. 80%, 90% you are producing water, and you have to abandon your well. You have to leave it for 1 year, and you have to wait till your water comes to lower degrees. In this situation, of course, what happens? There will not be any water oil contact. We can talk locally. We cannot talk about any water oil contact because it will be directly, your waters will have a tendency directly to reach your well, and oil could not be produced. So what happens instead of in these conditions? What happens? For example, one of the latest methods, electrical heating, they are applying. Okay, they are putting some in the well. They are putting some electrical devices and heating close wellbore area. And what happens? Heating resulted in having higher viscosity of that oil, and having lower viscosity, decrease the viscosity of oil. Because lowering the viscosity, it will be movable, and some. Okay, also deep angle question came up. Deep angle, I will explain. So which dry mechanism is the most productive? Actually, the question has to be which dry mechanism in which condition, we can say, okay? From one dry mechanism to another. Of course, what we can say, if you are talking about the pressure maintenance, water drive, if you have a good management, water drive is one of the best solutions. If you have an aquifer beneath your reservoir, this is very good. If you can manage it if you can manage it continuously, monitor your wells continuously, then it will be very easy and very beneficial to produce. Okay, but the question here in the question is, with which specifications we are talking about the dry mechanisms. Okay, this what I can say about this question. But so far, the aquifer is, of course, when you compare with the gas cap, aquifer is much more beneficial compared with that one. So, what about the deep angle? Okay. So deep angle, I think we discussed this one. Okay. So your reservoir dip angle, how can I describe this one? Your reservoir dip angle is a measurement of your permeabilities, your vertical and horizontal permeability. For example, you have a section with totally vertical, okay, or you have a section with some angle, okay. Your reservoir section I'm talking about, not well. I'm talking about your reservoir section. If you have a certain angle in your reservoir, so the ratio of your vertical and horizontal permeability will be different, okay. So high reservoir deep angle will be resulted having a higher permeability, okay. So this is actually is the angle of your it's described as the angle of your reservoir, we can say, okay, and the permeability behavior of your reservoir as well. Okay. Any more?
I think we don't have question.
All right.
So
So next week, for next week, we will, as I mentioned, we will mention about the multi-phase flow meters, which will be the latest technology devices actually. When we compare it, in the last 10 years, it started to develop. And we will definitely need these fluid behaviors, phase diagrams in the description, and how effective it's using. We are using the multi-phase flow meters. So this will be, this week will be totally combined with the next week topic. So try to come next week as well. All right. If there is no other question, then we can end the session for today. So thanks to all.
thank you very much. Also, students very thankful. So I think we can finish.
All right.
Thanks for coming and taking time for us. Thank
See
you.
you next week.
See you next week.